Scientists made Schrödinger's cat a grandma's. Because scientists keep asking, is the universe really so stubborn, forbidding objects above a certain size from being in quantum superposition? How small does something have to be both a particle and a wave? No, to be both particle and wave. Vienna used a new method, pushing the size limit. The study by grandma physicists was in Nature. They prepared metal clusters made of thousands of sodium atoms, weighing about 170,000 Daltons and 8 nanometers in diameter. That's equivalent to a large protein, a giant cat, in quantum superposition experiments. But at that weight, and under the experimental velocity conditions, the de Broglie wavelength is only about 10 femtometers. Trying to catch an interference signal with traditional double slits is impossible. Worse, these metal sodium spheres stick to physical gratings due to van der Waals forces like a gecko. The experiment would fail. The team used standing ultraviolet laser waves to build alternating bright and dark light walls, creating a 3-stage Talbot-Lau interferometer. First, to prevent environmental interference with the quantum state, these Römratter's vacuum chamber was 9 × 10 circumflex -11 MB bar, emptier than outer space. Then, the first challenge, a thin, straight particle beam. But the first of the 3 light gratings, G1, acts like a comb. Even if the incoming particle beam is messy, it can comb it straight, establishing spatial coherence, so they qualified for the next game. The second grating, G2, is the core and a death trap. If a particle hits a bright band, the light will ionize it. Then it's kicked out of the beam by an electric field and eliminated. Only particles that stay near the dark bands can remain neutral and continue. Wait, if the grating interacts with the particles, doesn't that count as a measurement? Why didn't the quantum state collapse? Indeed, for particles hitting the bright band, the quantum state did collapse, but they were also kicked out. For those that survived, we only know they passed through a dark band. But not which one. Lacking path information, the quantum superposition state is preserved. G2 doesn't just filter. The light field uses optical dipole forces to make the matter waves of the surviving particles pushed faster, dragged slower at different positions. This is physically called phase imprinting. The result is that the waves no longer act like a straight line, but begin to spread in multiple directions and overlap. The calculated superposition distance was 133 nanometers, 16 times the particle S size. This means it wasn't just a blur, but distinct, widely separated. Possible positions appeared. But how do you know it really took multiple paths simultaneously? Because the interference fringes after the second grating, those atomic density waves like a zebra crossing, are invisible even with Schrödinger eyes, so scientists set up a third grating as a movable sieve. Scientists scanned with the sieve. When holes aligned with high-density areas, passing particles soared. Move it slightly, and the sieve's walls aligning with high-density areas, passing particles instantly dropped. The signal showed high-low fluctuations. Still skeptical, scientists feared ordinary shadows or Moiré patterns. They pitted the quantum model against a classical explanation. It took 2 years and thousands of hours of data analysis to finally extract this precious regular signal. This is the ironclad proof that these sodium spheres are both particles and waves intertwined across the world. While not the most massive, this is the first time such spatially separated superposition has been achieved with such a large object. The macroscopicity index reached 15.5, an order of magnitude higher than previous records, proving that, for a giant 170,000 Dalton cat, the universe hasn't called cut. The cat can get fatter. When will we hit a wall? Will physicists hit it first? Will GTA 6 come out? Or will the government budget pass? Let's wait and see.